Without writing anything on the board, I'm going to tell you just a little bit more about linear algebra, which is great stuff. Okay? If you pursue anything with significant mathematical content, you will have at least a fundamental linear algebra course in your future. Okay. One of the really neat things about linear algebra, you've seen that if we multiply that matrix by that vector, that 800, 200 vector, okay, that we get something that we can represent by an arrow. So we get a vector, right? Okay. And we did that for a couple of vectors and found that the lengths were decreasing, right? Okay. So another property of stochastic matrices, does it always make the length of a vector decrease? You know, if the matrix has this form, does it always make the length of the vector it acts on get smaller? Okay? Good question. And right off the top of my head, I kind of think so, but I've never worked it out. I mean, I could prove it in a couple of minutes, but I'll kind of leave it for you, just in case we get to it. So yeah, there's a question you can kind of write down and work on if you want to. You could answer the question, you know the Pythagorean theorem, there's the form of the matrix. What does it do to the length? Okay? Now, interpreting the algebra is within your grasp, but challenging. Okay? Many of you, I think, could do it, and I couldn't pick out anybody that I don't think could do it. Okay? Well, the other thing I want to say, though, is that when you multiply the matrix by the 800, 200 vector, it turns it and shortens it, right? Well, what if you multiply it by some other vector? What's it going to do? Okay? What if you multiply it by a vector with negative components? Which doesn't really correspond to the real-world interpretations we're using here, but you can do it. Well, what it does is it does a combination of rotating space, because you saw how the vectors can rotate, right? And stretching or compressing space. Okay? Now, this particular matrix has eigenvalues 1 and 0.7. Okay? The eigenvalues tell you two things. First of all, they allow you to determine the eigenvectors, which are the vectors that stretch. There's a vector. There's a vector that stretches. But there's a vector that, if you multiplied by this matrix, would keep its same length and direction. Okay? There's some vector that's invariant on this transformation. Okay? And any multiple of that vector would be invariant. So in this one direction, space doesn't stretch or compress. Okay? There's another direction corresponding to the 0.7 eigenvalue, and not necessarily perpendicular. It's not almost not going to happen. Where space gets compressed by a factor of 0.7. Oh, well, you multiply your lengths by 0.7, so everything compresses in this direction. Okay? The result of that is circles become ellipses, and they get rotated and distorted. So all space gets distorted. Okay? And there's a basis for a lot of computer graphics. All right? And you can extend that into three-dimensional space, where spheres become ellipsoids, kind of like footballs, but more elliptical. Okay? Like big old blimps or something. And it gets really fascinating, and you can then generalize this into higher dimensional spaces. And that's a lot of what linear algebra does. And if you can visualize that much, you can visualize most of linear algebra. Okay? I did a response to a Reddit thing about visualizing linear algebra. I said, visualize what happens to the circle of radius 1. Visualize what happens to a sphere of radius 1. That's what happens in any dimension, except you can't visualize it beyond 3 dimensions. Okay, so it's very neat stuff. So just a blurb for something that might be in your future, and something that's kind of fun to know.